You know, when we talk about all these different companies that get hacked, right? You've heard about this every single month or something. Facebook, Equifax, whatever. They get fined, right? But does anybody, maybe someone loses their job, but did they lose the business? Does the business actually disappear? In this world of digital assets, security is much more than a discussion item. It's much more than a slap on the wrist. It is the business. It's an existential risk, okay? So if you can help these guys out, then we can definitely help all you out because your businesses will survive, unfortunately, if you do have that kind of incident. So, slides? There we go. Okay, so how many of you are familiar with digital assets? Show of hands. Yeah? What's a digital asset? Give me an example. Rafal, what's a digital asset? You should know the answer. Bitcoin, right? You've heard of Bitcoin, right? Okay, so Bitcoin is something, cryptocurrency. So that's something we're all familiar with. But there's other kinds as well. There's tokens. And tokens are, created for things that are generally illiquid, like artwork or buildings. You can tokenize securities, debts, and so forth. You can tokenize fiat through using stable coins. So there's a lot of different uses, and all of this is very helpful in terms of driving innovation in the market. But what's interesting about it is that while it's all super cool and it's super modern, there's some super interesting elements when it comes to digital assets that you might be surprised about. And that is, a digital asset, okay, is a representation of a tangible or intangible asset, but that representation is nothing more than what we call a private key. And a private key is just simply a set of numbers and letters, okay? And it comes also with a public key. Now, a public key is something like your email address. You would give that out, you'd get messages and so forth, right? But would you give out your password, right? Probably not. Well, the same thing goes here when you have digital assets. You want to make sure that you don't give away the private key because it's like a bearer instrument. Whoever has the key owns the asset. And so with that, we've kind of like gone back to the future in a sense, right? Where, back in the early 20s and 30s, when you went shopping for a place to store your money, your cash most likely, right? Because you didn't want to, maybe leave it underneath your pillow, you would say, okay, which bank has got the biggest vault, right? Today you don't do that, right? But there was a time when that really mattered, okay? And so today, instead of people actually storing their money inside of a vault in a big bank or perhaps under their covers or their pillow, they have these devices here. This is called a Trezor, and this is a Nano Ledger, okay? So this is basically the state of the market in terms of storing your crypto. People walk around with literally millions and millions of dollars sitting in their pocket on one of these little devices, okay? And I can tell you that backing these things up is quite problematic, and if I had more time, I can go into many different ways you could break into these things, but I don't actually have that much time. So let's kind of go into where the market is headed then. There is a shift to digital assets, and I'll tell you why. Because you can make a lot of money. Silvergate Bank in the US, okay, simply did this. They offered a bank account to hedge funds, family offices, high net worth individuals, crypto exchanges, and the like, right? By doing that, in 2 years' time, they went from $47 million of assets under management to $2 billion. $2 billion, okay? 97% of those deposits were non-interest bearing. Okay, so the cost of deposits was only like 11 basis points. So they're making huge amount of money without having to pay it back out in interest, right? Just because they can offer a bank account. So you're seeing, a lot of these, banks, and here in Singapore, there's quite a number of banks that are getting into this as well. Seeing a lot of movement. Now, it's not dramatic movement, but it's going. They're also seeing different movements into what's called decentralized finance. And this is an idea where you have what we call smart contracts, just simply automated code, if you like, that automates the whole process of lending and borrowing, okay? And these platforms like Dharma and Compound and others are very, very cool. You can make a lot of money and not have to do a lot of investment. As soon as you deposit some funds, you start making interest and you're good to go, right? What could possibly go wrong with that? Well, what you probably don't know is that the administrators of these systems, they're decentralized, because we all have to be decentralized in crypto, right? But they're still humans. And because they have access to the price feed, okay, they can control what assets are being put up for lending, what the interest rate is, what the collateral needs to be. But they can also censor transactions, okay? They can even steal the assets themselves. So, you really don't have any idea about who is going to get you, okay? And that's what we want to talk about today. So in IBM, we focus, certainly focus on the external hackers and trying to keep them out, right? But actually, all the clients that I talk to, it's about the insiders, okay? It's the administrators, it's the operators, it's the developers. Who's that developer guy, the millennial guy, right? It's that guy, okay? He's evil, you didn't know it. We can make him behave himself even if he is evil, and I'll show you how to do that in a little bit. Okay, so Mark talked about custody. So digital asset custody, what is that? Well, if I'm not storing my crypto and tokens in these little devices, I have to store them with somebody, okay? And that we have a whole market of different players. In fact, later this morning, we'll talk to the CTO of Hex Trust, who's sitting right here, Rafal. And what these digital asset custodians are looking for is two things. Today, the state of the market is the assets are sitting offline in something called cold storage. They're just offline, right? So they're safe because they're offline. But can you use them when they're offline? Well, it's kind of hard. Technically, you can. But if you do a transaction, it could take up to 24 hours. And when you do a transaction, some human has to touch the device, perhaps memorizing the part of the key and maybe colluding with their buddy and getting access and being able to do a transaction. So that's not good. So cold storage, generally speaking, is something we want to move away from to something we say on demand. We want assets on demand. We don't want them online all the time. We want them online only when we need them, and then put them back offline. Okay, so that's digital assets on demand. On the vertical axis, you have cryptocurrencies only, which is Bitcoin and Ethereum and some of these others. But more importantly, though, if you want to tokenize real estate, you want to tokenize this building and make some money off of it, you need the ability to do any kind of asset. Okay, so if you want any kind of asset and you want it on demand, you're going to have to do something different than what is the state of the market today. There's basically 4 technologies that will help you do this. Okay, the first is something I call it fancy math, multi-party computation. Can you all say that with me? Multi-party computation. That's the first thing you need to know. It's very hard to even pronounce the word. Okay, imagine the math that goes behind it. The next thing is what we call bespoke immutable policy. A lot of these manual processes, these insiders, they can get away with stuff because they can get away with stuff. But what if we constrain them to a workflow that is fully audited and you can't change the rules? Well, then that might change some behaviors as well. Thirdly, we have something called a hardware security module and apps inside of those things. We'll talk about what that is. And then finally, this idea of protected memory enclave. So this is basically, I'm online, but in a very protected state, and I can do a lot of cool stuff. Okay, so those are the 4 different technologies that are being embraced today by the market in digital assets. And the percentages off to my left, your right, are what I consider the relative value with respect to actually protecting digital assets. And you'll notice the one that's most important is the 90%, and that's really that which constrains the humans. Okay? We're going to look at each of these real quick. So in the old days, what we like to do to protect that private key is shard it, meaning I cut it in half, right? And I might take that sharded key and I might stick it in a couple different clouds, right? What could go wrong if I do that? What could I do wrong? Well, if I'm Paige Thompson and the person who hacked the Capital One in the US because she knows how to navigate AWS. Anybody from AWS here? Okay, good. Because of that, you can get access to potentially those keys. In fact, if you had access to the system that these keys were being reconstituted on, guess what could happen? You could actually get the key and do a transaction and steal all the crypto, and that's actually happened before, right? So the idea behind say it with me again, multi-party computation, I didn't hear you. Try again. Multi-party computation is this. I can take the keys, split them up, and leave them there. And the magic happens next is I can sign a transaction without ever bringing them together. That's what's cool, okay? So let's take a look. This is how it works. So I've got this policy. It's good. Tells me who's the approver. I've got a key management system telling me, what the rules are with the keys. I've got my sharded key over there. I don't need to bring it together. I can sign, even in an untrusted environment and do a transaction. Isn't that cool? Right? That's nirvana. But actually, is it? You know what an armadillo is? Armadillo? Well, it's got a harder outer shell, right? And it's got that squishy part underneath. Well, if you think of it this way, multi-party computation is kind of like the hard outer shell. It works. It works in an untrusted environment. But the stuff that's not so sexy is kind of the squishy underbelly. If you were an attacker, what would you do? What would you go after here if you wanted to get to the keys? Can I have some suggestions from the floor, please? Yeah? How many people would, raise of hands, how many people would go after the secure multi-party computation itself and attack that? Not too many. Okay, good. How about the key management system? Would you go after that? Yes, you would. Okay. How about the administrative approver policies? Yep, I might do that too. Okay, let's take a look. Oops, sorry. There we go. Here's our attacker. So yes, I would go and I would change the rules. I would change who's an approver, how long they have to approve, because I can, because nothing's preventing me from doing that, right? I can go ahead and change the rules with respect to the key rotation. Instead of every 15 minutes, I'll just turn it off because I can, okay? The actual MPC itself, I can, because it's a one-way street, meaning I can't derive the inputs from the outputs, I can actually redirect all that traffic to a malicious version. And finally, because the key parts themselves are generally created with something called low entropy, the random numbers are sort of weak, and they can be brute forced if you have access to them simultaneously. Okay, so there are ways to defeat this. It's good, it's cool, but it's not awesome. Okay, next. This is where the 90% comes in. How do I make these workflows auditable? How do I prevent people from changing the rules? So let's take each example. So transaction approvers. These are the folks, I want to do a transaction. Okay, I'm going to approve. It's usually multi-party, multi-quorum, right? What you want to prevent is any of these guys, or women, whoever, right, changing the rules and then hiding their tracks by changing log files and things like that, okay? So you want to make sure they cannot collude. You want to keep them honest. So the only way to really do that, or way we think you should do it, is define what we call an immutable policy, literally in code. And you run that in an encrypted environment, perhaps an encrypted memory, okay, as one way to prevent it from being changed. That way the rules have to be followed. The same thing kind of applies then for your administrators and operators as well. Instead of having one person controlling what user accounts are up to date or closed and what have you, we have administrators that have to follow distinct policy, and every single touch they make with respect to users and engagement of them in the system is all logged, and they can't change those logs, right? And then finally, when it comes time to authenticate, a lot of phones, like my iPhone, you guys have one of these? Yeah? This has a secure element in it. It has a private key and a public key. You take that public key and you hard code it into like a policy. Now you can tie a human to their phone. And then if you have things like biometrics or challenge questions, you can tie that specific phone to that specific human. And then if you have a second factor, you can use that as well. How many people use Google Authenticator, by the way? Okay? Don't. Google does not use Google Authenticator, okay? Use something here. This is called, consumer safety tip. FIDO2 compliant second factor, YubiKeys, although they've had their own problems. But YubiKeys are good for second factor. SMS, not good either. So anybody that uses a text message for your second factor, not secure either. This is just for your own health, okay? All right, so then the last thing is, once we've authenticated the users, we want to do that again, hard-coded, so that anytime any of this changes, I have to redeploy code. And you're saying, why would I want to do that? How can I do that? We'll talk about that in a minute, but it's actually important. Now, I mentioned earlier the third thing was these hardware security modules. How many people have interacted with a hardware security module this week? Hands up. Okay, how many people have taken money out of an ATM this week? Yeah, a little bit more than that. Okay, well, you've interacted with a hardware security module. That PIN code that you put in, that's basically where it's protected. An HSM is responsible for maintaining keys. It also generates random numbers of high entropy variety, and basically it is used to sign transactions. Okay, so that's pretty cool. Do you think HSMs were designed to run applications? No, they were not. They're supposed to manage keys. But we have companies out there that are trying to run entire application stacks inside of these little devices. So here's some things that you have to think about when you do that, mostly around maintenance. Okay, so if I have some blockchain events like a fork or an airdrop or something like that, wallet upgrades and what have you, I've got to do something about that. But you know what? It's offline when I have to make that upgrade. If I have a curve that needs to be changed, or perhaps the operating system of the underlying HSM itself needs an upgrade. Any one of these events causes you to be offline. Therefore, you need to have a backup. Well, if you have a backup, that means the private key is in multiple places. That itself is a security risk. The other thing, though, and this is a little bit scarier, actually, is when you have these applications running inside of an HSM, and you have your friendly evil developer show up, what they can do is they can actually take, let's say, the wallet application, insert some malware, and then deploy it back into the secure element side, and then they can start to leak the private keys and ultimately get them after a certain period of time, right? You know why I know this? Because Treasure, which is the manufacturer of this device, made a point to Gemelto. Anybody from Gemelto? Pointed out that Gemelto HSMs were susceptible to this hack. Okay? By the way, IBM's were not. Okay. So I mentioned earlier about needing to back things up. So that should be no big deal, right? You take your seed from one, you put it in the other, right? What could go wrong? If I'm an evil developer, I have an evil who works on networks. I have an evil network administrator. Okay? What can they do? They have special tools that can read network traffic. And yes, a high entropy, high random number is something easy to pick out. So they can get the key, and they can do a transaction. So that's not good either. So here it brings us to protected memory. All right? Now, what is protected memory? Well, it's kind of like, like a vault, if you will, that you run your applications in, right? And they automatically are encrypted as a result of doing that. And they're highly restricted in terms of the access, and we'll get into a little bit what that means. But 16 terabytes means you can do a lot of really cool stuff. You're not limited. Like, is anybody from Intel here? No? Because the only other competing technology is something Intel has created called software guard extensions. And as you can see, it's not exactly 16 terabytes. It's about 120 megabytes, which means you have to make a lot of choices. Okay, am I going to protect this piece of my code or this piece of data, right? And then I might need a whole bunch of them, so then I have to administer a whole bunch of them. Oh, by the way, because these things boot up in the clear, I can't store secrets in them. That's kind of a problem if you're dealing with crypto, right? So actually, it's not going to work. You need something bigger and better. And so what we like to do is we take all this stuff I just talked about, and we run it inside of these secure service containers. Okay? So we have our wallets, we have the multi-party computation, we also have our databases, our administrative policies, etc. And it's all locked down, and it's locked down by a master key that's sitting inside of our HSM. By the way, that's the only thing that we use the HSM for. We don't store applications in our HSM. We just store a master key, and we use that to encrypt everything. Okay? And that gives us the ability to then grab what we need when we need it, do a transaction, and put it right back. Okay? The other thing, too, is that when you talk about security, you don't want things to break. You want them to bend, right? So we have this idea of isolation. That's where the little red lines are. And that is something called, we call it Evaluation Assurance Level 5+. What is that? Well, Common Criteria has these different ratings, and 5 is basically, let's just say air gap, which means if I have, let's say that this is a computer and this is a computer and there's air between them, right? That's air gapped. But there's also a network, okay? And so if there's a network, you have an attack vector. What we have here in our terms of our isolation is that all of the communications are done through the firmware itself, the hardware, so we completely take that attack vector off the table. So they're that much more secure. Now, let's say that you are the administrator of this environment. You are the secure service container administrator, and you are evil. What could you do? Let's find out. Well, it turns out that if you are, in fact, the evil administrator, there's not much you can do because there's no command line. So I can't type anything, okay? There's no secure shell. I can't inject any code. I can't get any malware in there, right? Because I don't have the ability to do that. I have a whitelisted, what's it called, REST API that kind of prevents me from doing stuff. I have to basically follow the rules. And with this isolation, I can design my different applications in this environment so that, in fact, they bend, not break. And I can keep all of this in terms of the security of it in there, in this memory, because it's secure booted, all right? So you have monitoring, logging, automatic encryption. Anything you deploy into this environment benefits from this encryption, okay? So this gives you real-time online access to anything you want to do in a very safe and trusted way. So how could this be useful to you today? How many of you actually deploy applications? Okay, how about your firm? Do they deploy applications? Okay, if your hand's not up, it's highly suspect. Okay, highly suspect. Now, what I want to talk to you about now is something that you can use this technology for in your business today. Okay? Yes, we have it for, we've built this specifically for digital assets, but it actually applies to any kind of development process you have. So the idea here is you have your developer. Here's our developer. And we put our code in there, and we use GitHub, which is just a place to store it, right? Now, what will happen now is if I was evil, I'm the administrator of this environment, I could take this source code, I could make a build that has malware in it, deploy that, and who would know about it? Nobody, right? Except for this. There was just a small story. There's an app called Copay that was you can put on your phone, you can store your Bitcoin in it, right? Open source. Everything's great with open source, isn't it? Except when you have a malicious actor who inserts malware, and then you build based upon this open source with malware, and then you deploy it to all the different handsets out there, and then, of course, everyone starts losing their crypto, because that's actually what happened with the Copay hack, right? So you want a way to prevent the malware from ever getting deployed. So how you do that is you build the software image inside of, guess where? Secure Service Container. Okay? You sign it in there, and you have this thing called a manifest, which basically tells you where you got all the code from. Then you can push that out to some repository called like Docker, Content Trust, or what have you. And the administrator, your trusted privileged developer, they can't replace that image with a malicious one nor change it because they can't get the key because that's sitting in a secure service container, right? Now, if you're a custodian, that actually isn't good enough. Because if you're a high net worth individual and you want to trust your custodian that their internal processes are legit, you have to assume that the entire company is malicious. Rafal, you are malicious, okay? And your whole team is. But I'll still leave my money with you. You know why? Because you will get a third-party auditor, right, who will audit the build. So how do they do that? They will take the manifest that's in the secure service container, or I should say access it, see where the source code came from, right? And then you know that, in fact, the build used that source code, and they can do maybe a code review or something like that, maybe some pen testing, and then they have their own policy. When everyone is signed off, we have an endorsement service that will go pick up the build and deploy it into production. So you've guaranteed that there's no malware in your code. And what's more interesting about this is that there were no humans involved after you did the initial deployment into Git, right? It's all automated. So this is pretty cool tech. You can use it for anything, okay? Any kind of build. And it's available today.